Good afternoon, students, and welcome back to the physics classroom. Today, we'll be discussing a couple of topics related to the concept of laws of motion, that is, apparent weight when a person is traveling in a lift or elevator. We will discuss equilibrium of concurrent forces and a bit about connected motion. So, let's begin with the situation of a person traveling inside a lift or elevator. We will be talking about apparent weight and we will be discussing about the different situations. Suppose a person of mass m is standing on a weighing machine placed in an elevator or lift. The actual weight of the person is obviously equal to mg. This acts on the weighing machine, which offers a reaction R given by the reading of the weighing machine. This reaction exerted by the surface of contact on the person is the apparent weight of the person. We shall discuss how normal reaction R is related to mg in different situations. Let's begin with the first one, when the elevator is at rest. Then acceleration of the person is equal to 0. Net force on the person F, that will be equal to 0. Therefore, R minus mg will be equal to 0. So we can write down R to be equal to mg. That is, apparent weight is equal to the actual weight of the person. When the elevator is moving uniformly in the upward or downward direction, again in uniform motion, acceleration of the person is 0, because the elevator is moving with a constant velocity. There is no change in velocity with respect to time, so acceleration is 0. So in a similar fashion, we will again obtain R to be equal to mg, that is, apparent weight is equal to actual weight of the person. This is something that you can see in the picture. When the elevator is accelerating upwards, suppose uniform upward acceleration of the person in the lift is given by A, as you can see in the picture. Net upward force on the person F will be equal to m into A. M is the mass of the person. As it is clear from the figure itself that F is equal to R1 minus mg. So we can write down R1 to be equal to F plus mg. So this means R1 is equal to ma plus mg, or R1 is equal to m taken out as common a plus g. This means clearly R1 is greater than mg. Hence, apparent weight of the person becomes more than the actual weight when the elevator is accelerating upwards. When the elevator is accelerating downwards, suppose uniform downward acceleration of the person in the lift is given by A, then net downward force on the person F will be equal to m into A. Again, we can write down F to be equal to mg minus R2. So R2 will be equal to mg minus F, that is equal to mg minus ma, that is equal to m taken out as common g minus a. So clearly R2 is less than mg. Hence, apparent weight of the person becomes less than the actual weight when the elevator is accelerating downwards. Now, what should happen if acceleration becomes equal to that of gravity? That is the situation of free fall. In that case, R2 will become equal to how much? Using the same equation, we can write down R2 to be equal to m g, and now the acceleration is equal to g, so that will be equal to 0. That is, apparent weight of the body becomes 0 or the body becomes weightless. Now, weightlessness is felt only because the force of reaction between the person and the plane with which he is in contact vanishes. One more situation I would like to discuss at this point: when downward acceleration is greater than g. Let's suppose the elevator starts accelerating downwards with an acceleration greater than the value of acceleration due to gravity. That is, a is greater than g. Then what should happen? In that case, R2 will be equal to mg minus a, that is, R2 becomes negative. Apparent weight of the person becomes negative. In that event, the person will rise from the floor of the lift and stick to the ceiling of the lift. So, once more, I will like to discuss these two situations, that in case of free fall for a body under gravity, R2 will be equal to m g minus g, that is equal to 0, which is referred to the situation of weightlessness. This concept of weightlessness will be discussed further in the coming lessons. And if a is greater than g, then R2 equal to m g minus a will be less than 0, that is negative. In that case, I told you that the person will rise from the floor of the lift and stick to the ceiling of the lift. Let's now discuss a very important topic, that is equilibrium of concurrent forces. For that, we should understand what are concurrent forces. The forces which are acting at a point are called concurrent forces. These forces are said to be in equilibrium when their resultant is 0. Two forces acting at a point will be in equilibrium when they are equal and opposite. Refer to the picture that is shown downwards. Resultant of forces F1 and F2, that will be given by R. Let's suppose R is the resultant, that will be equal to F1 plus F2. When F1 is equal to F and F2 is equal to minus F, then R will be equal to F minus F, that is equal to 0. Refer to this picture. In this figure, three concurrent forces F1, F2, F3 are shown acting at O. In order to understand the concept better, we have to do a bit of diagrammatic completion. We have to complete the parallelogram OA C dash B and then join OC dash. Now, according to parallelogram law, OA vector plus OB vector will be equal to OC vector, OC dash vector, sorry. You may refer to the picture once again. OA plus OB is equal to OC dash. Now, let us do one thing. We add OC to both the sides. So, we will get OA plus OB plus OC equal to OC dash plus OC. Now, if OC dash is equal to and opposite to OC, then OA plus OB plus OC will be equal to minus OC plus OC vector, that is equal to 0. This means F1 plus F2 plus 3 is equal to 0. That is, three concurrent forces F1, F2, F3 will be in equilibrium when resultant of F1 and F2 is equal and opposite to third force F3. Also, we know from triangle law that three concurrent forces F1, F2, F3 are in equilibrium when they are represented by three sides of a triangle taken in the same order. Now, as you can see in the picture, F1 is represented by OA, F2 by AB and F3 by BO. Hence, the resultant is 0 and they are in equilibrium. So, in general, any number of concurrent forces will be in equilibrium when they are represented by the sides of a closed polygon taken in the same order. This follows from polygon law of vectors. Now, one thing is to be noted. When concurrent forces are in equilibrium act on body, the state of the body shall remain unchanged. That is, if the body is at rest, it will continue be at rest. Similarly, a body will continue to move uniformly along the same straight line if concurrent forces applied on the body are in equilibrium. However, when the concurrent forces applied on a body are not in equilibrium, the state of the body will change depending on the resultant of concurrent forces. Lamy's theorem. An important result follows when three concurrent forces are in equilibrium. This result was studied first of all by Lamy and is therefore called Lamy's theorem. According to this theorem, when three concurrent forces F1, F2 and F3 acting on a body are in equilibrium, then F1 by sine alpha is equal to F2 by sine beta, and that is further equal to F3 by sine gamma, where alpha is the angle between F2 and F3, beta is the angle between F3 and F1, and gamma is the angle between F1 and F2. You may refer to this diagram. Alpha is the angle between F2 and F3, beta is the angle between F3 and F1, and gamma is the angle between F1 and F2. We shall now discuss about connected motion. What does connected motion mean? Consider two bodies of masses m1 and m2 tied at the ends of an inextensible string which passes over a light and frictionless pulley. Now, here we shall assume that m1 is greater than m2. So, the heavier body will move downwards and the lighter body will move upwards. Let A be the common acceleration of the system of two bodies. Since the pulley is light and frictionless, therefore the tension in the string shall be the same on both the sides of the pulley. So, on the heavier body, the various forces are: number one, its weight m1g acting downwards. You may refer to the picture for this. Its weight m1g acting downwards, the tension T in the string acting upwards. So, as this body moves downwards with acceleration A, the net downward force on it is m1 A. So, clearly m1g minus T will be equal to m1 A. Coming to the lighter body, the various forces are again the weight m2g acting downwards and the tension T in the string acting upwards. As this body moves upwards with acceleration A, the net upward force on it is m2a. So we can write down T minus m2g is equal to m2a. So adding these two equations, we get m1g minus m2g is equal to m1 plus m2 times A. So m1 minus m2 times G is equal to m1 plus m2 times A, or we get A to be equal to m1 minus m2 divided by m1 plus m2 into G. Clearly, you can see that the acceleration is less than acceleration due to gravity. Acceleration of the system of two connected bodies is always less than acceleration due to gravity. Now, if we divide these two equations, then we will get m1g minus t divided by t minus m2g equal to m1a by m2a. You can cancel out a, so you are left with m1 by m2. So now on cross multiplying, we get m1 m2g minus t into m2, and that is further equal to m1t minus m1 m2g. So you can get twice of m1 m2g to be equal to t taken out as common into m1 plus m2. So now you get t to be equal to twice m1 m2 divided by m1 plus m2 into G. So hence tension T in the string can be calculated using this equation.